Everyone thanks everyone for coming, and welcome to the second session of our Lunch and Learn series on Agile Model-Based Systems Engineering. This is session number 2. Last session, session 1, we covered modeling and what does a good model smell like, what are some good attributes of a good model. You can go and still, if you missed that one, you can go and register and sign up and watch the video and download the content. This talk is being brought to us via Smith and Nephew, sponsoring the first couple of the series, and several chapters through the region have sponsored the remaining talks in the series. So the Lunch and Learn series is really going to focus around Agile Model-Based Systems Engineering for today. October, November, we're going to talk about use cases and requirements. Then November, December, we're going to do ICDs and handoffs, system to software handoffs more specifically. And then January and February is going to be testing and patterns and safety. So that's what it looks like as we run out the rest of the year. We did lock in our next dates. Our next date will be October 20th. We have proposed dates for the remaining 5, and we're going to send out a survey to all the registrants to find out what's the best days that work for everyone. Again, you can register and then come back and watch the video later. Not a problem. We are going to try to schedule it so that the majority of people can attend and we can have the good discussions and feedback at the end like we had last time. So the organizing and sponsoring chapters for this are the Three Rivers chapter, the Heartland chapter, the Michigan chapter, the Wright Brothers chapter, and the Canada chapter. So these are the main chapters out of the Great Lakes and North Central region that have organized and come together to provide the funding and the stuff to provide this series of talks. So who are we? We're the chapters of the Great Lakes region of INCOSE. And what is INCOSE? INCOSE stands for the International Council on Systems Engineering. It's a not-for-profit organization that's set up to disseminate the systems engineering practice, raise awareness, raise best practices, and make sure that companies via industry, academia, and even governments are taking systematic approaches to solving complex problems. We have 18,000 members throughout the globe, 74 chapters in 35 countries, and we do sponsor 55 working groups. And we have around 3,500 certified software systems engineers out there. For more info, please go and look at the INCOSE website. If you're not a member, please consider joining. INCOSE is broken up into 3 sectors. We're in the Americas sector, there's an EMEA sector, and then there's an Asia Oceania sector. And our region is right here in the middle. We have Canada, all the way at the top. We have the Heartland chapter, the Chicagoland, the North Star, the Midwest Gateway, the Great Plains, the Crossroads of America, the Wright Brothers, the Three Rivers, the Cleveland, Northern Ohio, the Finger Lakes, and the Michigan chapter. So these are the chapters that make up our region. We also, in addition to having co-sponsored, co-organized talks and lunch and learn series like this, we also have a conference that's coming up in December, which will be the Great Lakes Central Conference. INCOSE is steered by a corporate advisory board, and there's around 120 different corporate organizations that steer INCOSE, and these are representative government, industry, and academia. Please look and see if your corporation's here, and if you're not a member, you can sign up to be an associate member for free, which means that you get access to our website, a lot of our best practices, the SE handbook, and other things that INCOSE publishes as part of the working groups. INCOSE also has 55 different working groups and initiatives to better the systems engineering practice. Some of these range from transformational things like agile systems and systems engineering to application-specific domains like defense systems. There's a healthcare working group, which gets together and talks about healthcare, med device type stuff, and also enablers and transformational working groups. So these are all on the INCOSE website. You can go look at them, see what their charter is. They meet annually. sometimes more often than that, and they publish best practices, they take on challenge projects, and give concrete examples to follow. Please visit the INCOSE website, look into getting membership, joining a chapter or a working group. You can also find meetings and events. You know, as we always say, this is a volunteer organization. We're looking for more volunteers to help us out, help plan sessions, help work on you know, getting content put for our various websites and our various activities, and help organize. So if you're interested in helping, when I hear about a topic and help run it down, please reach out to Jack or myself or any of the other chapter leaders that are on the talk. So every one of these sessions, we're going to give out an autographed book from Bruce. Bruce autographed it. So Carolyn Booth won last time. She won for session 1. She's Systems Engineer 1 from Raytheon Technologies. And she's a 2021 graduate of Southern Methodist University in mechanical engineering. So congratulations, Carolyn. So stick around till the end. At the end of when we get to the questions and stuff, we'll look. Jack draws the name from the participants that are active, and you get an autographed book by Bruce, randomly drawn, and you got to be present to win the book. So without further ado, I'll hand it over to Bruce. So Bruce, Dr. Bruce Douglas has deep and broad expertise from over 40 years of experience, specializing in both model-based systems engineering and model-driven development for embedded software for safety-critical systems. He's developed systems in a number of subject domains, including aerospace, defense, medical, automotive, and telecommunications. He is a co-author of the UML and SysML standards, and is the author of over 7,000 book pages from a number of technical books, including Agile Model-Based Systems Engineering Cookbook, that's his newest one, Agile Systems Engineering, the Harmony, a MBSE design book, Real-Time UML Workshop for Embedded Systems, Real-Time Design Patterns, Doing Hard Time, Real-Time Agility, and Design Patterns for Embedded Systems in C. He's formerly the Chief Evangelist at IBM and currently the Senior Principal Agile Systems Engineer at the MITRE Corporation. So with that, Bruce, the virtual floor is yours, sir.
All right. Let me take control here. Okay, so welcome everybody to Lunch and Learn 2, Introduction to Agile and Model-Based Engineering. So we were chatting a little bit before the session started, and somebody mentioned that you know system engineers have been doing work for a while, and now they're told, oh, we're going agile. And what does that mean? Well, where do you go to find out? There isn't that much literature on how to apply this to anything other than 3 folks working in a garage developing a website. Really small, co-located, standard, business-oriented software. If you're doing real-time system, a safety-critical system, which may or may not include software, what does it mean to me, right? How do I address that? So I think that's a really interesting question. I've written on that. But really, if you look at the literature, almost all the literature about Agile is applying to this small, co-located software development team that's doing kind of standard business-oriented software like payroll systems or websites. So there's an open question. So I've done this for a while, working with a variety of companies to help them embody the principles of Agile thinking and Agile development to other domains, such as embedded and technical software, which has a whole host of separate concerns over kind of payroll systems, as well as system engineering. And that's what we're being focused on today. Now, in a lightweight way, we only have an hour, so there's lots of stuff I will not talk about that is really interesting stuff, but finite time. If you want to see the video, you can also go to my, not only to the INCOSE site, you can also go to my YouTube channel. I did post the video with permission from INCOSE to my website, or my YouTube channel rather. So there's that video is also available there, as well as some other stuff that occasionally wax profound about. So let's talk briefly about what do we mean by Agile exactly. So again, very lightweight treatment. Just talk about some of the high points. Well, one of the things we mean is incremental delivery. So rather than, the ideal delivery system at the end of, 5-year plan or 10-year plan or 3-year plan, whatever your maximum plan is. And that's the first time you actually start deploying the actual system. Rather, we do incremental delivery. So in systems, that might mean that you're co-developing hardware and software. So the first versions of delivery might be on simulated hardware because the hardware doesn't exist yet, or on some COTS hardware, which is not going to be the final. Later versions might be done on breadboards or wire wrap boards. Still later iterations might be delivered on prototype hardware until you finally get to kind of production hardware. All along the way, you are delivering incremental systems that do something, that do some set of behaviors, usually a subset of the overall behavior expected, but they do it well and in ways that delivers value to the stakeholders. One of the aspects of Agile is that, Agile is not so much about doing different things as much as it is about doing the same things in a more effective way, right? So the example I like to give is brushing my teeth. If I want to have really high quality teeth, I could say at the end of every year, December 31st, I brush my teeth for 12 solid hours to get me those high quality teeth. Or I could say, you know what, I will brush every day. I'll get quality that way by doing incremental, maintenance and quality delivery of tooth quality, right? And that's kind of what Agile does. Rather than say, we'll test at the end of this big overarching process and we deliver something in some number of years, we will continuously focus on demonstrable correctness. We'll talk a bit about that in this session. How do we do that with respect to model-based engineering? We're always focusing on what I've got so far. It may not be complete, but what I've got is demonstrably correct. So we're going to focus on correctness all the way through, rather than this notion that we'll just verify at the end. And of course, it'll work, just like it has never worked before. But of course, it'll work at the end because that's what our plan says it should do. Now, kind of the lean dimension of Agile says that you should do things that avoid unnecessary work. Do things where they add value and emphasize that, but don't emphasize things where they don't add value. And there are lots of times and places and processes where you're spending time, crossing I's and dotting T's that doesn't really add value. So should you be spending a large proportion of your time doing that stuff if it's not adding value? So we try to focus on where we can actually add value. And we frequently deliver that value so that's visible to stakeholders. We get feedback of not only is it correct, against, we talked about verification, something we talked about in the previous session, that it meets the requirements, but also meets the need. And so we can expose the stakeholders to these frequent deliveries and say, does this in fact meet the needs? Another notion is rather than have kind of weak stakeholder involvement, which is more traditional, it involves a certain kind of milestone points like maybe PDR, CDR, SSR, or SRR. Rather, we involve them all the way through, and you continuously get feedback as to are we still meeting your needs? Does this work for you? Does that work? Does that work for you? And so on. Rather than developing this theory that if I build a system with these properties, it'll ultimately meet the need, and not really test that theory until some number of months, years downstream. So continuously involving stakeholders, and finally doing what I call planning to replan. So rather than having this elaborate plan, overly elaborate plan, I've seen plans that say, okay, we're going to be done with this program in 2024, June 17th at 6:03 p.m. Well, you don't have the fidelity of information to really make a statement like that. But nevertheless, people do plan as if that was the case. Really, plus or minus 6 months maybe. And as you learn more, about the velocity, about the needs, about the technologies involved, you can reduce that uncertainty and get more and better. So you can replan, you can tweak your plans as you get more information, assuming, of course, you're paying attention. So you plan to replan. So you have a plan. So some people think if you're doing Agile, you're not planning. Not true. You do plan in Agile. You just don't entirely believe your plans. You don't entirely believe your marketing hype, right? So that you'll do a plan with some error bars on it. And as you learn more, the error bars shrink. You become more precise in terms of expectation, either because you know more about the velocity, know more about what you're trying to do, know more about what satisfies the need, know more about what the technology can deliver, and so on. So you plan to replan. So there's certainly other aspects of Agile we haven't talked about, but those I think are the kind of 6 kind of key bullets. So we satisfy business need, produce a system meets a need by creating demonstrably correct work products, applying effort where it yields the most value. That's what we do. And one of the key kind of underlying ideas here is you should always be close to being able to demonstrate the correctness of what you have so far. You can always just, for minutes from now, I can say, let me show you why this is right so far. Or if it's an error, let me discover that and fix it now. There's a law of Douglas, which says the best way not to have defects in a system is not to put defects in the system. It's not to find them later, but rather don't put them there in the first place. And these practices are largely focused on how do you do that. Let's talk a little bit about the Agile lifestyle. So we talk about, we have project planning, so the overall, kind of either the product line level or the individual product level, where it's going to go in the next several years. And we get this product backlog of things that you want to do. As we plan our iterations and allocate functional iterations, we do iteration planning, and then we allocate subsets of the product backlog into the iteration backlog. And this is, in terms of time scale, what I call in the Harmony process, the macro time scale. 6 months on, whatever the scope of the project, 6 months, 18 months to 24 months, whatever your particular project might be. So larger scale, kind of strategic kind of planning. So the next level down is what we call the iteration or sprint kind of life cycle, where you do this cadence. Typically, it's anywhere from a week to 4 weeks, where you incrementally build these deliveries of versions of the system with particular missions in place. And you elaborate your use cases, epics, user stories for this purpose. You verify your systems you produce against the requirements, and then you have a retrospective that says, how can we improve our work? How we're providing value? How can we improve? And that's what I call the the micro time scale. And it's a single iteration, typically one to 4 weeks. And finally, at the kind of nanocycle level, we're doing things like daily meetings. We have this design, implement, test, kind of nanocycle. It might take you 20 minutes to an hour, and you have continuous integration as you achieve this kind of stable, correct status of engineering data, engineering information, and work products. You integrate them together, and it's on an ongoing, continual basis, and avoid that kind of big bang integration at the end. And this is what I call the nano cycle, and it's anywhere 20 minutes up to a day for doing that kind of delivery. An hour is probably a pretty common time frame for a nanocycle. And here we focus on what I call minimal verifiable feature. If I'm building a model of something, what is the minimum change I can make to it, which then results in a kind of significant step towards verification of the overall goal. Right? So this is the kind of time scales that I think of. And together, these concepts form what I call the Agile life cycle and lifestyle. Now, in the developing embedded systems and software-intensive systems, we have a number of specialized concerns. Specialized hardware. You have to do custom device drivers. You can use off-the-shelf device drivers and maybe develop new algorithms. For that, you have hardware and software co-development. You have constrained tools because your execution environment is different than your development environment, which is unlike kind of standard software, where we use cross compilers and to get to the target hardware environments. So we have different development versus kind of target environments. We have a lot more need to specify predictability, timeliness, safety, reliability, security concerns. And we have standards conformance. We have a lot of specialized concerns for this kind of environment. And we will meet those with an application of various different practices for Agile methods. Now, we're going to tweak those to be particularly relevant given the technology we want to apply. Model-based engineering is kind of focus of this entire Lunch and Learn series. And we'll talk about some set of these practices in this talk. I don't want to go through this in detail. You can look at download materials after the fact. But the idea here is that the rows of this table are the different concerns that you have from the previous slide. And the columns are the different practices. And different practices that address different sets of concerns. So you select the practices based on how important the various concerns are to you, by and large. Now, I don't want to talk about all those, right? We don't have time. So I'm going to focus on just 7 practices. So we're not going to talk about like pair programming. We're not going to talk about stand-up meetings or how to do reviews or how to do spikes and risk management. Those are all really interesting topics. We're not going to talk about how to do agile planning and product planning poker, and those are really interesting practices. Finite time. So I wanted to focus on some agile practices that either are unique or tweaked for model-based engineering. Use case and user stories, simulation and computable models, verification-driven modeling, the handoff from systems to software, which is probably the question I get asked most often by system engineers. How do we effectively hand off the work we're doing here in SysML or in a model-based environment to downstream engineering? Not just software, but electronics and mechanical and hydraulics and other kinds of engineering disciplines. Also want to talk about design patterns, defensive design, and a bit about architecture and what I call a 5 views of architecture practice. So I plan to answer questions towards the end. So feel free to post them. And I know that Dan or Jack will read those out to me at the end. So feel free to post. So first of all, let's talk about use cases and user stories. So the purpose is to characterize stakeholder needs through understanding the interactions of a system with its environment. Often users, hence the name user story, but any kind of elements in the environment we typically call actors, some of which are human users, some of which may be external systems with which we must interact. So user stories are a tool that we use to capture description of the software feature in terms of this kind of end user perspective. How do we interact with this? I want this thing to happen for this purpose. User story helps create a kind of simplified description that describes in a small number of requirements. So we often capture it in this kind of canonical form, as a role, as an actor role, pilot or maintenance engineer or navigator. I want this feature to achieve some goal, some purpose that I have in mind. And this allows you to then refine and understand the requirements so you can understand, am I building the right system to meet the needs? I'll make the argument later that user stories are roughly equivalent to scenarios from a kind of use case model-based approach, but either it can be used, and I have in fact used both. So some examples of user stories. As a pilot, I want to control the rudder of the aircraft using foot pedals so that I can set the yaw of the aircraft. Okay, this is fairly straightforward. but it's missing a lot of detail. What accuracy, what fidelity, what time latency, and so on. As a power supply, I want to provide constant power at 15 volts, plus or minus some range, with a current of 5 amps, plus or minus some range, to power the rotor. And you can see that as you start adding detail in this kind of canonical form, it starts becoming awkward to say. As a navigation system, I want to report the position of the aircraft in 3 dimensions with an accuracy of plus or minus 1 meter every half second, so I can fly to my destination. So it's a way of thinking about it, about the problem. And each one of these then have a number of more detailed, shall statements, requirements that specify what it is that you need here. So there's this kind of canonical form. As a user, I want features so that something I want happens. Some objective that I have as a user is achieved. So how does this relate to the other concepts you often see in UML, SysML, and elsewhere, epics, use cases, and user stories? And how do I relate all these things together? Well, this is how I think about it. There are competing opinions, and that's okay. Diversity is an okay thing. But I'll tell you how I found it useful to think about these things, classify these things in real projects. So first of all, we have an epic. An epic is this coherent set of features, use cases, user stories at a strategic level. An epic, kind of almost by definition, cannot be achieved in one iteration, requires multiple iterations, generally from 2 to 6, but you can fall outside the range. To complete what a Scale Agile framework calls a program increment. And epics come in a couple of flavors. You can have a business epic where it delivers kind of functionality, or you can have a technical epic where it delivers kind of infrastructure or refactors or reduces technical debt or something like that. Now, an epic contains multiple use cases. So one aircraft design in Canada I worked on, we had a military aircraft and we had an epic, which is to be able to track tactical objects. And it took like 7 or 8 iterations to implement. We broke it up into quite a number of use cases about delivering that. So this is kind of an included relationship between the epic and the use case. The use case is composed of a few to many scenarios and or user stories. And roughly you think about it corresponding from a few requirements up to 100 requirements. So that's kind of scope. A use case can typically be implemented in a single iteration. And several of them collectively form then an epic. Now, use case itself includes smaller organizations of things. Scenario is an interaction of a system with a set of actors. So you think about a particular set of inputs that arrive in a certain order with particular values and particular timing, and there's some output or outcome. And that's a scenario. And if you change the values, the inputs, the timing or sequence, that changes, that's a different interaction. So the scenario roughly corresponds to interaction. It's roughly equivalent to a user story, which talks about, as a human pilot or navigator, I want to use this feature for this purpose. It's roughly equivalent in terms of size. So I think of them, you can use them in some sense interchangeably. In my experience, scenarios are better for more complex things, but user stories can be used for more simple, straightforward interactions. And all of these elements then include requirements, multiple requirements, then the star means a bunch of. So everything on a scenario for requirements capture represents a requirement. If I send a signal or perform a behavior, it's there to realize some set of requirements. So there's this mapping between the scenario and the requirement, or between the user story. There's a bunch of requirements about controlling the rudder for setting the yaw of the aircraft. A bunch of requirements about that. So there's some relationship there. And I will talk more about this in the Lunch and Learn 3, epics, use cases, user stories in more detail. And then how to analyze those in a model-based environment is the subject of Lunch and Learn 4, improving system requirements with use case analysis. So we'll talk about more about this later, but this is a practice that I use a lot in my systems work. The next practice is simulation and computable modeling. So the purpose is to understand a process, system, or design without having to construct the actual thing and use it kind of, in anger, kind of in the actual operational environment. Because it might be expensive, it might be, you want to use it as a predictor, you want to use it to solidify your requirements. It might be inappropriate to do so. What happens if we explode this bomb here? You might not want to do that experiment, but you want to study the effects. So you can use simulation computable models to understand something. You can always use it to understand, a set of requirements. I build computable requirements models all the time. They'll be subject of Lunch and Learn 4, how to actually, pull that off. The simulation is an imitation of an operation of a process or a system. To do so requires, well, guess what? Executable models. So to do that, you have to have a well-defined description, both in imperative and declarative aspects of a model that represents key characteristics that are relevant to the questions asked by that model, its behavior, functions, or physical properties at an appropriate level of precision. So you don't necessarily need to go down to the transistor behavior level. You may in some cases, depending upon the question you're trying to answer, but you have to pick a level of precision appropriate for the kinds of objectives of the simulation model that you have. This is a topic we talked about in the previous Lunch and Learn session. So in this context, we have many uses for simulation and computable models. I talked about doing requirements models and execution to refine my requirements, understanding how an architecture works, executable architecture, executable designs, automatically generating software source code from a model. I've worked with some people doing automatic hardware development from a design model as well. That's not so much done with UML, SysML. Well, it is done in things like System C and VHDL. Evaluate various quality of service requirements and properties like performance, safety, security, and reliability. So just to be clear, I do draw a distinction between execution and simulation. An execution is the performance of behavior, whereas a simulation is an imitation of behavior. And so you'll hear me talk about elsewhere about how simulation is a weak form of execution. That's what I mean by that. It doesn't have all of the properties. You say these are the core properties I want to simulate, and that's fine. But an execution is actually the performance of the behavior. So I do draw a distinction there. So here's just an example of a computable model. This is done in Rhapsody tool. So video start going. So in the upper left-hand corner, we've got an estate machine. This is for a traffic light control system from an intersection, a pretty simple model. And the magenta color illustrates the current state of these different, and states in this case, whereas the green illustrates the last state or transition being taken. On the right-hand side, we see a sequence diagram. It's called an animated sequence diagram. It's drawn as the simulation progresses, as the computation goes on. It captures what goes on in the interaction between these elements in a sequence diagram. And in the bottom left-hand corner, we've got what we call a panel diagram, where you can use, in this case, these LED lights to show the current states of these various elements involved. I can insert different events of interest, like a primary car arrives in the turn lane or the secondary turn lane. And so I can simulate different situations. I can even do entire test cases by inserting events in a sequenced way in these other buttons as well. So I can control and visualize the simulation to answer questions of concern. What happens if this is going on and then a primary turn lane car arrives? At what point is the car handled? Is it ignored? Is it properly dealt with? And I can do that to understand the system rather than look through dozens of pages of requirements and say, I think this does what I want, as opposed to actually what it might actually in fact do. That's just a very simple example case. Come on. There we go. Another practice which relies on simulation execution practice is verification-driven modeling. And even people who use executions often build the entire system and say, oh God, I hope this works. And then they spend a long, long time trying to get it to work. I remember one company, I was asked to come in and consult. I got this phone call, oh my God, we're all going to die, kind of phone call. And they had this system, they had this element. They had 800 states in the state machine, and they had spent some long period of time putting it together. And now they're trying to get it to execute and to run. And they had spent months trying to get it to run. They basically were tearing their hair out. So they called me. So came and looked at it, and it's this huge kind of mess that had been grown without ever doing a simulation execution along the way. So at the end, then they've got the 800 states with maybe 1,200 transitions, and they're saying this doesn't work, and we can't even get it to begin to run, let alone partially execute. Can you help? So the first thing we did was we basically threw it away, and we started over doing this verification-driven modeling effect, where we our practice, where we built this up in like 20-minute to 30-minute increments, this kind of minimal verifiable feature. Get that to work, and then we'd add more stuff. And so in the course of a week, I was able to work with their team and build an entire complete system model that did what they wanted it to do, where they'd spent months trying to get this big monolithic model they had constructed getting to work. So the purpose is to improve quality through continuous verification, such as testing and execution of your model. So we build models and make them executable, and we execute them frequently. I'm talking about, like I say, every 20 or 30 minutes kind of time frame, not just after the fact, not just after we get it and say, oh God, I hope this works. So I'm not relying on prayer as much as engineering to get it to work. And this results in early identification and removal of defects, resulting in higher quality work products and higher quality models. So to be effective, we want to do this a lot. So in the courses that I teach, we'll build, reasonably complicated models in the course of a simple, 3 or 4 day course. But we do this, in these little small increments, build this much, get that to work. And then once that's working, then we add more stuff to it. This kind of minimal, verifiable feature concept. Similar to test-driven development, but for models. And we have these little nanocycles as we construct that. The next practice is the one I get most questions on is how do I hand off system engineering data from a model-based engineering environment to downstream engineering, which includes software, although it gets most of the attention, but also electronics, both analog and digital, hydraulics, pneumatics, mechanical systems, chemical, nuclear, and other engineering disciplines. So there are a number of reasons why it's difficult to hand off. It's different vocabulary, different tools, different ways of thinking about things. But we do need to find a way of handing off the engineering data. System engineers are doing the work for a reason. We're going to find ways to hand it off to achieve goals in such a way that it's consumable by the target engineering staff, downstream engineers, and it's also retains the information content without loss, either in precision or in terms of content. So we must understand, of course, everyone on this call probably does, that system engineering is completely different from software development. This is not something that's well understood in some environments. I know that in IBM, where I was chief evangelist, there was a large contingent of people who thought that system engineering was just a kind of software development because of the kind of focus that IBM has. And so it was, that argument occurred in many hallways in many continents over the years. We focus on system engineering on system properties, independent of the engineering discipline that will implement them. And later on, kind of towards the end of that process, we start do what we call the deployment architecture. We start allocating them to different disciplines. To hardware, software, architecture designs, and we need to be able to do that in an effective way. So you can do it monolithically in a traditional process, V-cycle process, ka-chunk, you hand it off. But that's really just a degenerate form of an incremental process where you just do one increment, right? And we want to specify a number of things such as interfaces between systems. Typically in system engineering, you have a lot of logical interface development. At some point, you have to refine it to physical interfaces because the subsystem teams are going to do actual physical systems. So you have to understand the physical interfaces. And we have to allocate into the deployment architecture, as I mentioned, the different engineering disciplines to get the software and electronics and mechanical use cases, user stories, and so on. Also, you want to define interdisciplinary interfaces. How does the software talk to the hardware? It gets most of the press, but also the interaction between electronic and mechanical systems as well. So this is the workflow. We're not going to go into too much detail. On one side, we're building what we call the shared model, which identifies the physical interfaces and the physical schema of information passed along with those interfaces between these subsystems, which are interdisciplinary. And then within the subsystems, we want to identify their properties, the contributions of different engineering disciplines to their goals. So this subsystem may be electronics and mechanical. This other one may be mostly software and electronic, with some mechanical. So different mixes of different engineering disciplines. The contribution of an engineering discipline to the mission objectives is what we call an engineering facet. So the software facet, the electronics facet, and mechanical facet contribute value to the overall system or subsystem objectives. And we allocate requirements to those engineering disciplines and define the deployment architecture and the disciplines, the interdisciplinary interfaces between those facets. This will be the topic of Lunch and Learn 6 in some detail. We'll talk about how to do this. Design patterns. The idea here is that the problems you solve today are often really similar to the problems somebody else solved elsewhere. And a design pattern is an abstraction of that solution away from its specific context, so that it can be reapplied in different specific contexts, right? We abstract the solution, that's the design pattern, which we then reapply into similar problems in other specific contexts. So they're generalized solutions to commonly occurring problems. Formally, they are parameterized collaborations. Collaboration is a set of object roles typed by blocks in SysML that collectively work together to achieve some higher level purpose. And the parameterization means that there are places where you can instantiate different solutions or design patterns. And that's what we mean by instantiating a design pattern, is substituting elements of the design pattern for those parameters in the collaboration. So design patterns optimize properties. So all of design really, I think, is an optimization problem. We select one design over another design, even though they both meet the functionality requirements, because one design is optimal against aspects that we care about, such as performance or latency or maintainability or time to market or some other aspects. So we have these different kinds of elements. We have the formal parameters and we have these kind of glue elements put together. And there are four primary features: applicability, where it applies, what it optimizes, solutions, and then consequences, pros and cons about using this pattern over some other pattern to solve the same problem. And I talk about it in a couple of my books. Here's a really quick example of this. Here's a system for a train that uses an optical sensor on a wheel. So you've got a crosshatch mark on the wheel that spins around. You've got a light source, an optical sensor. And as you get the change in reflection, and given the size of the wheel, you can say, oh, the train is going this fast. Okay, that's what the optical sensor part of it does. And then from that, you determine train speed. That's shown in the middle here. And there's a couple of clients. In this case, a speed controller for closed loop control of the speed. And then we have a text view for maybe display on the car, what going to how fast is the train going in different cars. They have multiple text views here. So we want to optimize this against maybe against bus bandwidth. The way this is set up as the train speed changes is basically has to know who it's connected to and send these information off. So it's on some property basis. Well, how do we decide that? How do we optimize that bus traffic? So we look in our pattern literature and say, the observer pattern does that by adding a few abstractions here. We've got this subject who has information that we want. And then we have observers that need that information. And they can subscribe. And when they're subscribed, you get a notification list of all the subscribers, notification handles. And then when the data meets some criteria, like it's updated or every so often, we walk the subscription list and notify the subscribers. That's how observer patterns work. Then we can instantiate this pattern by bringing those elements. So train speed is now a subtype of the abstract subject. And so it inherits the properties of notify, subscribe, and unsubscribe. And it has a list of notification handles because it inherits that. Text view and speed controllers are both subtypes of observers. So they now know how to subscribe, and they have a notification operation. It's notified, when the data changes, when they're notified of some change. And so this is then our refined design patterns. That gives a very, very simple example. There are lots and lots of design patterns that are relevant to real-time and safety critical systems. That's kind of where I focus. Look at my stuff to see more about that. Another pattern that I spend a lot of my time on is called defensive design. The notion of defensive design is that we want to improve the robustness of our systems, not just our software, or our systems, to unexpected events and conditions. So correct functionality always depends upon some assumptions, some invariants. Defensive design codifies these assumptions in the design so that you have assurance that if the assumption isn't met, you take appropriate corrective measures rather than just failing in interesting and unexpected ways. We'll fail gracefully, or we will handle it and keep on delivering functionality and value. But that's a subject of the particular patterns that we're doing. Whether it's okay to fail in a graceful way, or whether it's there's a way to log the error, take some sort of corrective action, and then continue to proceed. So there does require some additional work, both design work and also runtime work. So additional work at runtime to compute cycles, but it provides additional robustness. So typically you want to have input parameters. So for example, let's suppose we're delivering, we have a patient ventilator which delivers drugs based on the mass of the patient. And for some reason, the mass of the patient is wrong. It could be because somebody entered wrong. They meant to say 100 kilograms, they entered 1,000 kilograms. It could be because it was corrupted via EMI. That happens all the time in operating rooms. It's a very high EMI environment. I've seen it change actually in operating room environments personally, as I've been involved with managing systems. So we'll be able to detect, oops, that's wrong, and do something correct rather than kill the patient and have a postmortem to figure out why that happened. You want to make sure input values are in range, output values are in range, value sets are consistent. If you say this person is a neonate and you're saying they're 100 kilograms, well, that's kind of inconsistent, right? So the data sets should be consistent. You want to make sure resources are available, and what happens if they're not available? What do you do in that case? You have the system state is compatible with a request. Maybe C or Cs are valid. Exceptions are handled properly. Error conditions are handled properly. and determine what corrective measures should be taken if my invariants are violated. So Grady, a friend of mine, had a statement that I really liked. If we built houses in the same way we built software, the first woodpecker would have destroyed civilization. And this goes to the fact that many of the systems, most systems that we create are pretty fragile. If you use them in very particular ways, they'll work properly. But as soon as you start having novel circumstances, novel inputs, violating those preconditions, things go bad fast in unexpected ways. And really, I think that we should build more robust systems. And to do so requires this practice defensive design. So let's look at an example. So redundancy in the small. I'll talk about redundancy in the small. That's kind of low-level checking. For example, here we've got in a medical system, maybe you have an O2 source, and it's got value properties like volume of gas remaining, the chamber pressure, and flow rate. And then we've got some operations like set flow rate, and this implementation is just you pass in F and you set the flow rate to F. Simple implementation. Get minutes remaining. Well, you get the volume remaining divided by the flow rate, and that returns that. And get the flow rate, just return the value. So that's the naive implementation, let's say. We could subclass that now and say I've got a safe version of that where we ensure our preconditions are set. So the idea is whenever I set a value, I compute a 32-bit CRC, cyclic redundancy check, and store it. Whenever I read the value, I recompute the CRC and make sure that it still applies, it's still valid. And this will detect, for example, EMI failures or memory fault. Those detect those kinds of failures. So for example, if I get minutes remaining, it'll say, okay, if the CRC stored CRC is equal to the computed CRC, that means there's been no EMI or no inadvertent or memory fault, right? Then if the flow rate is greater than 0, well, I'm not sucking oxygen out of the person, right? I'm putting oxygen into the person. So flow rate should be a positive number. Right? So if it's greater than 0, then I say I compute my flow rate. Otherwise, I have a fault, 0 flow or less than 0 flow, or I've got corrupted data. So every time I invoke this service, I'm going to check my expectations are in fact true. And you can make this arbitrarily elaborate in terms of the checking. For setting the flow rate, first thing I make sure is that things are correct. And if it's in range, so it's less than maximum flow rate and greater than 0, then I set the flow rate and I recompute and store my CRC. Otherwise, I throw an exception because something's bad here. So again, I add these extra checks to ensure that my system remains valid, even if something went wrong. And then we've got architecture as the last practice. So I've got this practice called 5 views of architecture. So we want to represent the structure at the strategic level of design as a collection of design patterns from different aspects. And the idea is that an overall architecture is an integrated interlocking set of patterns from each of these 5 different areas. And yes, there are other areas of concern, but in my experience, these are the 5 really critical areas for our systems. And your environment may add a few more of these. So we have these 5 different areas. We'll talk about these in the 5 different views shortly. So some key points about this. We do want to avoid big design up front. So rather than design everything about architecture up front, but we do want to define a set of an architecture, a set of interlocking patterns, even if we create it incrementally. So as we go through our iterations in an agile way, we will add more and more aspects to architecture and more patterns and more different particular specific features to optimization of our architecture. We do start off with what we call architecture 0. So there's a thing called iteration 0 in agile methods. It's what I call the work to do before there's work to do. So initial building up your team, creating your development environment, thinking about the overall system vision. Before we start building real systems, we want to sort of create an environment for creating the real systems. As part of that, we have architecture zero, the stake in the ground for where we expect certain architectural aspects to end up. And this may change over time, maybe refactored or modified as we discover more, but this gives us our starting point. It's called architecture zero. I'm a big fan of using UML and SysML for that. And these architectural work becomes technical work items in our backlogs. So an architecture is really, to my mind, is an integrated set of design patterns from these different architectural aspects that collectively optimize the system at a strategic level. So some quick guidelines about building architectures. Architect early, right? So even if you start with an incomplete architecture, just some aspects and some relatively low level of precision, start there. Evolve it frequently. So every time you do an iteration, you might have some increment on your architecture as well as some technical work items. Simpler is better. So if you have multiple patterns that optimize equally well, select the simplest of those options. Again, I believe in pattern-based architectures because we want to reuse, prior experience, prior success in building systems. These become technical work items in your backlog that will be allocated to your iterations. All of these optimize properties of the system at a cost you're willing to pay. That's what a good architecture is. It optimizes things at a cost you're willing to pay to get that optimization. So it's trade-offs. Represent it in a model and model it. Don't just rely on oral tradition. And finally, you do have to keep your architecture current. An old architecture is no longer valid, doesn't really add a lot of value. So let's talk about these 5 key views of architecture. First of these is the subsystem component view of the architecture, where you identify the large-scale pieces of the system, the responsibilities, and the interfaces. And usually, to my mind, I don't have a software subsystem and a mechanical subsystem. I have a subsystem. And some combination of engineering disciplines contribute to it achieving its goals. You may have a system which is entirely mechanical, and that's okay, but I don't set up, there's the mechanical parts, they form the mechanical subsystem. That's not how I think about things. It's a subsystem which has some kind of functional goals in the context of the system itself and has a set of responsibilities and ultimately implements them using some engineering work, software, mechanical, electronics, and so on. The concurrency and resource view identifies what are my concurrency units, what are my resources, how do I map them into the semantic units, into the concurrency units, whether they're task threads or processes, I don't care for much at this level of abstraction, how I schedule them and how I manage my resources. And there's a whole bunch of design patterns on how to do that. The deployment architectures I mentioned identifies the involved engineering disciplines, allocates responsibilities to those disciplines, creating facets, and defines the interfaces that cross those disciplines. Distribution architecture focuses on the distribution of semantic services across different compute nodes, whether they're different cores in a multi-core system or different processors connect over a communication protocol. It applies to both of those things. And then we defined how those systems will communicate, collaborate, what middleware will be involved, and so on. That's all part of what we call the distribution architecture. And finally, the dependability architecture focuses on the identification, isolation, correction of faults or attacks as the system runs through the management of redundancy. They're all about redundancy management to identify things. And this has 3 pillars: safety, which is freedom from harm; reliability, which is a stochastic measure of the availability of services; and security, which is robustness in the presence of attack, basically. So, oh my God, are there more practices than this? But finite time, we won't talk about those in this session. But there are other practices about incrementally adding traceability, management of single source of truth, risk planning, using metrics to improve your project execution, control, and enactment, all kinds of other practices as well. So if you want to know more, come on down to my website. It's all free. Some resources here and elsewhere. With that, I'll pass control back to, I think Dan was the one who was controlling the meeting. So Dan, your turn.
All right. Thanks a lot, Bruce. I have numerous questions in the email, and I took a note as to what slide they were on. So do you want to jump back in slides while I ask them, or you just want me to ask them? And
I can do that, sure.
Okay, so we had a question all the way back on slide 7. And let me scroll to
All right.
So the question was how to deliver value to users / stakeholders when using simulation / prototypes for incremental delivery.
Well, simulation ultimately, I talk about that in practice up here. Simulation ultimately is an execution of some kind, right? It's an imitation of an operation. So you need to have an objective. If you're doing something like red-blue force mix, using AFSIM, for example, for Air Force simulation, you need to think, well, the objectives are to determine, is the force mix adequate? What do I need to model? What do we need to represent to do that? If you're looking at adequacy of requirements, you need to determine, well, what are my objectives? Well, I want to set these set of requirements. Do they really describe the feature here that I'm trying to meet, the capability I'm trying to represent? Or are the missing requirements, or are the requirements ambiguous or wrong? So you want to represent those explicitly. So it all gets down to be clear about the objectives and the purpose of the simulation, and model all those aspects at an appropriate level of precision to achieve that goal.
Okay. Thanks, Bruce. You can stay right here on this slide. There are a couple questions. It starts off, hello, Bruce. Thank you for amazing content as always. What do you think is balanced between prototyping and architecting in advance and trade studies? We use models because we can't exercise all scenarios due to limit of resources, but with less costly prototyping, 3D printing, automation, new materials, we can do more with prototyping. Do you think that systems development process, even including entire engineering, should be like software, fast deliverables, small teams, etc.?
Okay, I think there were 3 questions in there.
Yeah, there's a couple.
Yeah, so small teams, typically, in my experience, are easier to organize and have measurable progress with. Larger teams tend to be a little more difficult. That's why we have the notion of sprint of sprints, team of teams, right? That sort of thing. But basically, I think it gets back to be clear about the goals. It may be better to do prototyping if that's cost effective and timely. On the other hand, you might want to do something really early where it would be not cost effective to do a prototype. Even when you go to prototyping, what is the level of fidelity required for that prototype? You need to be really clear about that to make sure you meet the objectives. You do run the risk, if you're not clear about it, of solving the wrong problem or solving the problem at the wrong level of abstraction or precision. So you don't really answer the question. And so ultimately, that's the question. Just on a correctness basis, I would prefer prototyping because it's the real thing. You're doing execution of a prototype. With simulation, you're imitating a behavior, right? But it may not be cost effective. And with adequate care and work, you can do simulation to whatever level of precision is necessary to meet your need. So I think it's a continuum. But again, be clear about your objectives.
Okay. Follow-up question, that same one. With Agile teams, we have small independent teams. Do you think MBSE through descriptive system modeling will help to eliminate Agile issue with siloed teams?
Yeah, that gets to a practice which I call single source of truth. And the idea is rather than have siloed truths, we basically got replicated information using different formats and level of precision, accuracy, and so on. And then if they differ, the question comes up, which one is right, right? Instead, you have this federated set of models where you federate against a single source of truth, which then can be interpreted in different contexts to solve your problem. So yes, you can do that, but you have to plan for it. And some of it, there's the cultural aspect and technical aspect. The cultural aspect can be difficult to address. I think that that's true. But the technical aspect can be relatively straightforward by creating a federation of models. And they don't have to just be UML SysML models. You can federate, AFSIM or Jove or Mandelica and different, simulate different kinds of models that are good at different things and build a federation of those models to answer your questions. Oh, I hope that answered the question.
Yeah, thanks. Let's jump to slide 14. And Dan had a question about what do you mean by physical interface? Okay,
so physical interface. So first of all, let's talk about a logical interface. A logical interface talks about the logical properties. So for example, you have a radar and you want to get a radar track of something in the environment, in the airspace. So you have this radar. And you might model it as, so I send here's a radar track signal. Along the signal, I pass a radar track, which identifies things like combat ID, range, three-dimensional velocity. So you've got this information you're passing with the signal, but you model it as an asynchronous signal sent and followed by here's a radar track signal received, right? That's how you model it. That's a logical interface. When you actually get to the aircraft design, you might say, you know what, we're using 1553 bus. And here's a radar track really comes down to these three messages on the 1553 aircraft bus with particular, Indian, big Indian, little Indian format, what I call bits on a wire. And they'll be structured to 1553 bus messages. It's no longer an abstract, signal in SysML sense, but it's bus messages. And the data schema that describes the structure and content of those messages are part of what I call the physical interface. Whereas the fact you identified a signal with this kind of abstract data structure is what I would call the logical interface. So when we start refining the information to include physical properties, such as bits on a wire, timing between bits on the wire, big Indian versus little Indian, those are what I consider to be physical interface characteristics.
Okay, I think that definitely answers that question. Andrew had a question. Do you have a reference with a set of design patterns? Are these typically domain specific? How can we find some common domain patterns?
Okay, so
oh, right there.
So my books focus on this problem domain. That's where I focus on. Most patterns are more general than that. So we've got the real-time design patterns book and the design patterns for embedded systems in C. Also, there's a book called System of Patterns by Frank Bushman and others. It's a series of books on kind of systems patterns as well. And they focus, the first book is just general kind of structural patterns, but there's subsequent books that focus on different aspects of system design. So a System of Patterns from Frank Bushman and others is another series that you can go to for more information. Also, you can also Google design patterns. Okay, last time I did that, I got 4 million hits. So there's hits out there, but there are resources out there.
Gotcha. Okay, thanks. So how do we execute Agile / MBSE with global teams?
Well, you need to have a shared environment where ideally you can check out and lock models from that shared environment. I think that's the best way. You can also copy and then merge. Yeah, you can do that, and both in Cameo, because you work cloud, we can do branches and merge downstream. But really, Cameo to our cloud primarily is used, in my experience, as a checkout with lock, and then check back in when you're done. So ideally, you have a shared environment where you can check out the work product from, a web-based environment. But you can also replicate models in different environments. If you don't do that, you have to do that if you're working in skiffs, for example, and then merge downstream in an integrated model. So that's where you have to, and then you have to resolve incompatible differences. Rhapsody does this as well, with its kind of CM feature set. You can manage it. Ideally, the most simple case is, a model-based repository that's available off the web with check-in, check-out facilities built in.
Yep. Okay, thanks. We have one more question from the chat here, and then I'm going to jump to a couple that were asked before, although John did have a question. Cameo or Rhapsody, depending on complexity? Question mark.
I like both tools. Now, remember, I'll say it right up front, I've been working with Rhapsody since 1995. I was one of the team members that helped create Rhapsody, right? So I might have a natural inclination towards that. But there are things I really like about Cameo. I like the drag and drop. I like the tables. There are things I really like about Cameo. I would say if execution is really important, Rhapsody wins. If code generation from the models is important, Rhapsody clearly wins. In cases where those aren't so important, then you have to look at the feature set. I mean, either one could be used. I like both. I really do like both tools. But where detailed execution is really important, Rhapsody, to my mind, is the better tool for that. And that's my experience.
Okay, thanks. So one other question, do you think that systems development process, even including entire engineering, shall be like software, fast deliverables, small teams, etc.? This could be driven with introduction of less expensive and faster systems development, 3D printing automation, new materials, great simulation capabilities, and software-rich systems. Most of the new complexity systems has significant amount of software, i.e. software-driven. So I think that's more of a question of where do you see systems engineering going?
So I think the agile teams working in a distributed way, producing value against this integrated single source of truth data model architecture is the way I think things are going to go. But you have to do what makes sense. A big part of agile is doing what makes sense, and the notion that we do it exactly this way because dang it, we're agile is stupid. Okay, do what makes sense. If I'm designing the nuclear response for the Air Force, there's a different host of concerns I need to concern, and rapidly just trying stuff out might not be the best approach. I'll get to that. If I'm building a wristwatch, might be. So I really have to do what makes sense in terms of precision and move fast and break things. Depends on what is the consequence of breaking things, right? So I think you have to do what makes sense, but largely, yes, I do see that as a trend for development because in many ways it's better.
Okay, thanks. How do you balance responsibilities between system architects and developers in agile teams? I've seen teams that take agile to the extreme, and SMEs make all the architectural decisions.
I normally use the term SME, subject matter expert, for people who are domain experts, not people who are technical experts. So if a SME for a medical system would be the physician who understands the medical physiology and knows how to do the operation. They would be a horrible person to decide how to architect my anesthesia system. Okay, so no, they don't get to decide the way that I want to architect, my gas mixer and my patient ventilator and my vaporizer for my inhalant anesthesia. They don't get to decide that. They're not the right person to make that decision. Neither is necessarily the person who's writing device drivers for some of those systems. They're not the right person to architect. All these different areas do require specialized skill sets. Now, one of the ideas behind Agile, which I disagree with, from the kind of the three guys in a garage view, is that everybody can play every role. And you don't really need specialized roles. And that's just not true. People who understand how to do PID control loops are not the same people who know how to build user interfaces. And they're not the same people who know how to do detailed device drivers. Those are specialized skill sets. You need to use those skill sets in different ways. And so that's the difference between kind of, writing a payroll system and building an aircraft. There are specialized roles, and your systems need to be cognizant of that. Now, the degree of that cognition relies on the nature of the system you're building. In some cases, it might be more like a payroll system. Everybody can do everything. But the truth is somewhere in the middle, and the middle moves around depending upon the nature of the system you're trying to construct.
Okay, thanks. That tees up one of the questions that I saw that was submitted before. Bruce, there are a couple people that are apparently reading this as their book of the month club. Must be a pretty boring book of the month club, but they're reading your new book as part of that.
That would be an exciting book of the month club. I want to point out. Sure. Go
Depends
ahead.
on your perspective, I guess. But they noticed that you don't mention Scrum. And in reading this, I paid attention closely today, and I didn't hear you mention Scrum either. Why is that? You care to comment?
Okay, a couple of reasons. One is, if you look at the Scrum literature, it doesn't mention real-time embedded systems at all, anywhere, ever, right? So they don't really talk about systems stuff in Scrum, really. You do talk about it in SAFe, a Scale Agile framework, which I did mention. Mm-hmm. But Scrum itself has, all the literature is around the development of kind of typical IT software. And so I talk about Scrum for that. It doesn't mean that Scrum doesn't apply. What it means is that it doesn't talk about how it applies. So it doesn't talk about, so if I want to modify Scrum to apply to, development of bicycle gears, good luck finding that literature to help you out, right? So you'll have to decide, how do I need to extend Scrum for that purpose? So Scrum is a particular methodology which focuses on IT, what I call IT software. Can you use it? Sure, but you've got to make a lot of decisions on your own. How does it apply? So when I talk about it, I don't talk about that specific technology. I talk about Agile in general. And how do I do these Agile practices to meet my needs in the embedded and the systems space? So that's why I talk about Scrum specifically. Not that it's bad.
Okay, thanks. That takes us to the end of the questions. And we're at the end. Is there Peter Taslimi on still, by chance? Peter, if you are, could you come off mute, because you are the winner of the book for this session? I'm not seeing a Peter. Okay, we'll go to the next winner, Shelly Higgins. Shelly, we have your contact info. We'll get in touch and you can pick out a book and we'll send it to you in a couple weeks.
Oh, thank you. That's pretty awesome. I'm hosting a book club here at Raytheon Technologies. And since my department has already paid for a book, I know that there are book club participants who do not have a book. So I will gladly share the book with them. Thanks so much.
Okay, awesome. Awesome. Thank you for coming. So thanks everyone for your attendance. The next one will be on the 20th. And we'll send out a survey to lock in the dates for the last 5 then. So thank you all for your time and participation, and have a good afternoon.
Thank you very much.